Hey everyone, it's Athena X. So in this video, I want to provide a quick visual for the probabilistic setup from the previous video and provide some extra intuition about why we choose to model noise as Gaussian. Okay, so let's start with topic 1, Gaussian noise visualization. So if you remember from the previous video, the setup is that we want to find a best fit line. We have some random variables xi, and we have some random variables yi, which equal beta 1 xi plus beta 0 plus epsilon I, where the epsilon I, each of them are normal with mean 0 and variance sigma squared, and they're all independent. And actually, in fact, the set of all the xi and the epsilon I for all I are all mutually independent. So for each xi, you have an underlying y plus noise. So if you draw it out, you have some model that looks like this, okay? And you have some true line like this with a bunch of observations that look something like this, right? Cool. And as a reminder, the Gaussian PDF looks something like this. Now remember from probability that if you have a random variable and add a constant to it, the distribution gets shifted by that constant. So if we think about the PDF of yi given xi for a certain yi given xi, and let's also say that we are given the betas. This is the setup we had in the previous video. We got to a point in the MLE where we wrote it in this form. When you're given the beta 0, beta 1 xi, this term here becomes just a constant. And so yi is just epsilon I shifted by this constant, which means that what this means is yi given xi, also the betas, is normal with mean beta 1 xi plus beta 0. And the variance is still sigma squared. So I want to sketch a visualization of the distribution of the yi given the xi. So what does that look like? Well, see here in this example, for this normal distribution, the x-axis here is maybe some random variable, call it z, and this is the PDF of z, right? Of like a little z. So this is actually little z, you know, what z can be, and this is the PDF at that point. And so if you look at this line here, see these are some x's and these are some y's. And let's say for a given x, let's say I pick x1, and this is the underlying y1, right? But really, you get some spread. You can get anything in here. And if you think about what is the y-axis, it's all the values that the random variable y could be. So I could think of this y-axis, so this slice right here, as a kind of axis like this. And I want to, along this axis, I want to draw the PDF of y, but I'm going to try to draw it in the z-axis coming up out of the page. So it'll look something like this. And there's arrows to mean it goes on forever. And this will be it'll be centered on this point. So this yi is a Gaussian where its mean is actually on the line, but you're realistically going to get any yi on this axis. But you know, this drawing isn't that great, so let me copy paste in an illustration. I've cited the source, it's Fabian de Blander. It's in the video description and I've linked it. Hopefully this provides a bit of a better picture of what the model is. For some x, say x0, you have some underlying y, which is the mean of the true yi, and the yi has this spread. And you can think of the yi as coming anywhere along this axis where its probability is proportional to how high this PDF is. Okay, on to topic 2. Why model noise as Gaussian? Based on my research, there are a few reasons. First of all, it's pretty convenient and leads to solutions that are tractable and work in practice. In addition, there are statistical methods that evaluate how Gaussian noise is, and it turns out that noise often is pretty Gaussian. A more theoretical reason noise is often modeled as Gaussian is the central limit theorem. The central limit theorem, or the CLT, says the following. Suppose you have n independent and identically distributed random variables. IID here is short for independent and identically distributed. Suppose also that these variables have a finite mean and a finite variance, call them mu and sigma squared. The sum of these random variables is also a random variable. And as n gets larger and larger, the distribution of this sum here approaches a Gaussian distribution with mean n mu. So, as informally as n approaches infinity, this is distributed approximately normal with mean n mu and some variance. The variance is not super important right now. This is a really cool result. Why? Because we don't make any assumptions about what the distribution of the xi are. The xi could be binomial, exponential, or anything with finite mean and finite variance. But with enough samples, the sum of those xi converges to a Gaussian distribution. So how does this apply to real-life noise? Well, the central limit theorem holds for independent, identically distributed xi. But it turns out there are variants of the central limit theorem which hold for non-identically distributed, non-independent xi, though they don't exactly guarantee convergence to a Gaussian distribution. But they say that as long as the xi are not too dependent and have finite means and variances, the sum looks at least kind of Gaussian. So instead of this IID, you might have some kind of other assumptions. But as long as these aren't too dependent and they have finite means and variances, this sum will still be kind of normal in the limit. Okay, so how does this connect to noises? Well, in many situations, the total noise can be thought of as the sum of many small noises. Even in a small system, maybe some small circuit or a box with a thermometer in it or something like that, there's this unknown noise from each atom, from each molecule, and maybe the battery and the sensor and how the sensor gets to your computer and all that stuff. And as you go into larger systems, the noise can become more and more abstract. But you can think of the total observed noise as basically just being a sum of all of these smaller sources of noise. The idea is that enough of those noises will be independent-ish and with finite mean and variance that the sum of all those noises, which is the final observed noise, will be pretty close to Gaussian, at least for modeling purposes. So to recap, you can think of a system as having a bunch of individual noise sources, which are random variables. As long as those source noises have finite means and finite variances and are somewhat independent, their sum will be at least kind of Gaussian. This sum is the final observed noise, so modeling the observed noise as Gaussian makes some sense. Okay, and the final reason that Gaussian noise makes some sense is if you assume a finite mean and variance, the Gaussian distribution is the distribution with the maximum entropy. The definition of entropy and the intuition is a whole separate discussion, and there are lots of sources and videos about it, but at a high level, entropy measures the unpredictability or surprise factor of a distribution. Let me describe this with a quick example to show the intuition without a ton of math. So suppose you have a coin that can flip either heads or tails, each with a probability of half. So there's some entropy here. You never know if you're going to get heads or tails. But instead, if you flipped heads with probability 1 and tails with probability 0, now you have no entropy because there's never any surprise. You always know you're going to get heads, and that's exactly what you see. On the other hand, if you had heads with a probability of 0.99 and tails with a probability of 0.01, then you have some entropy, but not quite as much as in the half and half scenario. So here you expect to see heads almost all the time. And when you see a tails, you are surprised, but it's kind of counterbalanced by the fact that the vast majority of the time you would not be surprised. You would see heads as you expect. So this has a low but non-zero entropy. Now that was a discrete example, but noise is continuous. Continuous distributions also have entropy, and in general, just like in the discrete case, the more spread out a distribution is, the higher the entropy. So in this discrete case, there was you can think of a bar graph. As you had heads, you had tails, and there were two bars. And when the two bars were equal, there was the highest entropy. But if you had one bar that was very high and another one that was very small, that would be a low entropy situation. But similarly, even if you had a continuous variable, some variable x, if it could be uniform over some range, maybe from 0 to 1, you had a uniform distribution like this, this would have lower entropy than a distribution that was more spread out. Maybe it was uniform over the range from 0 to 2. This would have a higher entropy because there's more unpredictability. It can be any of all of these values, not just restricted to these values. I know this continuous example is kind of different from my discrete example. In the discrete example, when I made the distribution more spread out, I split the probability mass more evenly between heads and tails. But I never added more outcomes than just heads or tails. In this continuous example, however, when I made the distribution more spread out, I actually increased the range of the random variable. It used to take on values from 0 to 1, but now it takes on values from 0 to 2. Either way, the intuition stays the same. Spreading out a distribution makes the entropy higher, and you can prove this, but we won't in this video. You can prove that if you assume the noise has finite mean and finite variance, the normal distribution with that mean and variance is the highest entropy distribution out of all distributions with that mean and variance. So let's say you want to model noise, and you don't know its true distribution, but you want to be somewhat conservative and make the noise as unpredictable as possible, but still assume it has a finite mean and variance. Well, if you use entropy as your measure of unpredictability, then it's provably true that you should model the noise as Gaussian. Of course, finite mean and variance is also an important assumption, but it seems like this holds true in most real-life situations. So again, what I mean by max entropy distribution is the highest entropy distribution with mean mu and variance sigma squared is the normal distribution with mean mu and variance sigma squared. Okay, hopefully that gives you a better understanding of why we chose the probabilistic setup we did in the last video. Until next time.